In fact, the problems get worse and worse for special relativity. Einstein says, not only is it the case that pi changes because the circumference is shrinking but the radius is staying the same, but time is going to present problems. He says this, so too, we are unable to introduce a time corresponding to physical requirements indicated by clocks at rest relative to the rotating frame. The moving observer will be obliged to define time in such a way that the rate of the clock depends upon where the clock may be. Why is that? Well, just imagine little clocks on your spinning disk. Well, at the center, they're not moving at all, and at the circumference, they're moving quite fast. So these ones are running slow, but the ones in the center aren't. So the whole thing is breaking down the conception of a rigid armature of rulers with coordinated clocks at every point. We can't think that way anymore, says Einstein. We therefore reach this result. In the general theory of relativity, space and time cannot be defined in such a way that differences of the spatial coordinates can be directly measured by the unit measuring rod, or differences in time coordinates by a standard clock. There's a breakdown of our picture of special relativity. In light of this breakdown, Einstein does what he always does when he finds that clash among fundamental physical assumptions. He introduces a principle, and here it's the principle of general relativity, Einstein. So there's nothing for it but to regard all imaginable systems of coordinates on principle as equally suitable for the description of nature. There is no one set of coordinates that we can assign, that we have to imagine events described in many different systems that give them different coordinates, and each of them has to be just as good as every other one. That's his task. Now, getting there had been an extremely difficult task. It constituted what he often reported as the hardest work of his entire life. In the end, Einstein created a theory that took what other people thought to be simple and made it complex, and what other people thought was complex and made it simple. Poincaré, for example, a master of non-Euclidean geometry, remained persuaded to the end of his days that you would always keep Euclidean geometry and make the laws of physics more complicated. Poincaré knew perfectly well that you could redescribe physics with non-Euclidean geometry, just as he had redescribed branches of mathematics in terms of non-Euclidean geometry and made progress. But he thought that would never be true for physics. It would always be worthwhile to keep Euclidean geometry and to make the physical laws more complicated. Einstein came down on the other side. He kept the laws of physics completely simple. An object simply travels along the shortest distance between 2 points. But here's the rub. For Einstein, the geometry changed. The disposition of matter in the world, of mass energy, changed the geometry. It bent space-time so that calculating which path had the shortest distance between 2 points became complicated. The geometry became sophisticated. It changed which kind of non-Euclidean geometry it was, depending on how much and where the different mass energy clusters in the universe were. But the law of physics, the fundamental law of motion, that an object traveled along the shortest path, that stayed supremely simple. It was essentially Descartes' rule from the 17th century. It travels along a straight line being the shortest line between 2 points. But calculating that became complex. So Einstein flipped the assumptions of Poincaré again on their head. Instead of making the geometry simple in Euclidean and the physics laws more complicated, he kept the physics laws simple and allowed the geometry to become a more complicated and variable version of non-Euclidean geometry.